Hi folks, this first video of the last part of Unit 1 is about vector components. This is the moment in the course where we start to consider things in 2 dimensions instead of 1. And so vector components, in reality, we live in a 3-dimensional world, and so every vector can be represented by 3 components. In this course, and in most introduction to physics courses, you would pretend that everything can be represented in 2-dimensional space. And so when we say that, we say, well, basically pretending that everything exists on a piece of paper, on a flat plane. And vectors in our world of 2-dimensional space, we consider them to each be made up of 2 components. They are perpendicular. Each component points along one of the major axes as if you're graphing something. So I mean, this set of axes here says north and east, but basically what we're doing is we're taking every vector and we're thinking about it as if it's a set of instructions. First, you go this far in this direction on the x-axis, and then you go this far on the y-axis. It's exactly like plotting points, where the point you're plotting is the end of the vector. So let's look at what that would be. Vector A here is something I made up. It's a displacement vector. It's 6 meters at 55 degrees north of east. So in the summer assignment, you had to deal with this. So just a quick refresher. East is the reference direction. So east is where we begin. And then what we want is the direction that is 55 degrees north of that. So we start east and we rotate 55 degrees toward north. And so very approximately, we would have an arrow that looks like this. We could label it A. The length of that vector would be 6 meters, according to whatever scale we set up, and then the 55 degrees would exist there. And so that's what the vector looks like. And what I want you to understand is that every vector in our world of AP Physics 1 can be broken apart into 2 components. So just imagine that you're walking this straight path from the origin of our graph to the end of the arrow. Alternatively, you could give someone instructions that say, well, first you're going to walk a certain distance east, and then once you get there, you're going to turn and you're going to walk a certain distance north. And these are referred to as the components of a vector. One component will always be directed in the horizontal axis, which is the x-axis. And then the other component will always be directed in the vertical axis, which is the y-axis. And so that's how we think about vector components. Really what you're doing is you are drawing the base and the height of every triangle, and you're making everything a right angle triangle. We're eventually going to use trig, so that's part of it, but really we're just showing how much to the right or left of vector points and how much up or down of vector points. We're doing that separately. And then the magic of setting up a right triangle is that you can use trig to determine the magnitude of each component. So I'm going to redraw very roughly this triangle that I've made. I'm going to relabel it. We have the 55-degree angle. The hypotenuse here, A, is 6 meters. The base of this triangle is the x component of that vector. So it's how much to the right or left that vector points. And then AY is up here. That is how much up or down it points. And so again, just think of components as like 2 instructions on how to make a vector. One is left and right, the other is up and down. And every vector in 2-dimensional space can be written like this. So I'm just very quickly going to run through the trig as a reminder. We'll do some more practice in class, and you can ask me questions. But I can determine each component. So AX is the horizontal component of this vector. If I look at where it is adjacent to that angle. So I can say the cosine of an angle is equal to the adjacent side over the hypotenuse. So cosine 55 degrees equals AX over 6 meters. And if I were to multiply both sides by 6, oops, I could find the value for AX. So AX equals, and so very important in every physics unit we are going to put our calculators in degree mode, and I'll go over that in class. But if I do 6 times the cosine of 55, I get 3.4 meters. So the magnitude of the horizontal component of vector A is 3.4 meters. It just says go 3.4 meters to the right, and that's how far to the right vector A goes. AY is the opposite side. Again, I talked about this in the summer assignment, but you have many options now. But I always like to use sine and cosine. It gives my brain a little bit less to do. I still have to think, but I have a little less to do. So sine of the angle equals the opposite side over the hypotenuse. So the sine of 55 degrees equals AY over 6 meters. The benefit of doing sine and cosine together is that the algebra is the same. So I just multiply both sides by 6 again, 6 sine 55, and I get 4.9 meters. So these components give me instructions for building this vector A. I would go 3.4 meters to the right, and then I would go 4.9 meters up. And so if we're talking about like two-dimensional motion, when someone does this, if they walk just along vector A, they're doing both of these displacements at the same time, 3.4 meters to the right and 4.9 meters up. I want to do one more example. If this sounds easy and you want to try it yourself, go ahead and pause it and try it. But I think it's worth watching because there's a couple things that this vector has that the other one doesn't. So this first vector B, or the second vector B, is 14 meters per second, 30 degrees west of north. So if you want to very quickly draw your cardinal directions, we have north and we have east. The reference direction here is north, and we are rotating 30 degrees to the west of that. So I'm going to point my arrow this way. All right, so B is that way. Now, to make this vector, again, I can make it go how much to the right or left, how much up or down. I'm going to do this in a different order. Because it's west of north, I can imagine that I would go this far north. That would be BY. And then this far west, and that would be BX. I'm going to put theta down there. What I want you to notice is that theta now points towards the horizontal component, whereas in our previous example, it pointed toward the vertical component. So finding BX would go as follows. BX is opposite the angle. So I would say sine of 30 degrees equals BX over 14 meters per second. And so BX equals 14 times the sine of 30, 7 meters per second. So that's the first thing that's different about this vector, is that it points up, it opens up instead of to the side. And so for me, my horizontal component is opposite the angle. So don't get in the habit of using cosine for every horizontal line. You have to think about it before you do it. So sine and cosine might do different things for different vectors. The other thing is BX quite clearly points toward the left. So this vector BX is actually negative 7 meters per second. If east is always the positive direction, then BX is pointed in the negative direction. So west and south are still negative. Very quickly to find BY, I would now use the cosine of 30. That's going to equal BY over 14. BY is going to be 14 times the cosine of 30, and that's going to be 12.1 meters per second. That is positive because that's pointed up on my graph, or north, and so I don't need to modify the sign for that one. So finding the components of vectors is the first stop in learning two-dimensional motion.